So first we want to define the UMP, the uniformly most powerful. So let C be a class of tests for testing H naught, where our sample mean is an element of the parameter space, versus H1, where our sample is an element of the rejection space. And so a test in class C with a power function of beta theta is a uniformly most powerful class C test if the power test beta of theta is greater than or equal to the power test of beta prime theta for every beta prime theta that is a power function of test in class C. Or in other words, you can see this graph I have here with multiple distributions, and we can see that in this very first space, this is where we have our beta theta, and over here with this second distribution, we have a beta prime theta, and we can see that beta theta is in fact greater than beta prime theta. And so since we can confirm this, we know that we have on our hands a uniformly most powerful test. Okay, so I found a Neiman-Pearson lemma proof online that made a little bit more sense to me than the book. So I'm going to make a couple of substitutions here, kind of like in my last exam. So let's let W be our critical region, and so we can see that right over here. Here is our critical value, and dividing our W complement and our W critical region, where we will prove the alternative hypothesis by rejecting the null hypothesis. And of course, this orange shaded region is alpha. Okay, so if W is equal to the set of X, an element of our sample space, such that the likelihood function, or likelihood function 1 divided by likelihood function naught is greater than K, and the complement of W is such that X is an element of the sample space where the likelihood of function 1 is divided by the likelihood function naught is less than or equal to K. And so we've made a small little substitution here. Rather than using f of x given theta 1, we'll be using L1, and rather than f of x given theta naught, we'll be using L naught. Also, the book had it set up such that f of x given theta 1 is greater than k of f of x given theta naught, and here we'll simply make the substitution by just dividing both sides, or not the substitution, we'll just manipulate this by dividing both sides by f of x given theta naught, and this is how we're getting our L1 and our L theta. Proceeding, then W is the most powerful critical region of the simple hypothesis such that H naught for theta is equal to theta naught, and the alternative hypothesis such that theta is equal to theta 1. Then we will consider two possibilities. The probability that X is an element of W, the acceptance region, of given that H naught is true, is actually equal to the integral of L naught dx across W is equal to alpha. And so this is actually proving our sufficiency from the book. And then consider the probability that X is an element of the acceptance region given that the alternative hypothesis is true is greater than or equal to the probability that X is an element of the W1 acceptance space given H1 is true. And this is our necessity from the book. Since W is the critical region of size alpha, we know that the probability that X is an element of W given H naught is equal to the integral of L naught dx is equal to alpha. And the power of the region is the probability that X is an element of W given the alternative hypothesis is true, which is equal to the integral across W of L1 dx is equal to 1 minus beta. So to prove this lemma, we will prove that there doesn't exist any other critical region such that alpha 1 is less than or equal to alpha, which is more powerful than W. So consider my graph here to the right, we have what would be our critical region just typically, and then critical point, and then let's call this critical point 1, such that we have alpha in this space and alpha 1 right here. And so we want to let W1 be any other critical region, so this will be our W1, such that alpha 1 is less than alpha, and our power is 1 minus beta 1. We can now say that the probability of X is an element of W1, given H, the null hypothesis is true, is equal to the integral across W1 of L naught dx equals alpha 1. And similarly, we can run this through to say 1 minus beta 1. So to prove W is the critical region, we're going to prove first the probability that X is an element of W1, given the null hypothesis is true, is equal to the integral across W1 of L naught dx is equal to alpha 1. However, so note we've already proved step 1 by the definition, because we have already defined the probability of X element of W1 given the null hypothesis is true across the integral of L naught dx is equal to alpha 1. Alright, so we must now prove step number 2. In order to prove the probability of X is an element of given H1 is greater than or equal to the probability that X is an element of W1 given H1, it is enough for us to show that 1 minus beta is greater than or equal to 1 minus beta 1. So let us show two overlapping distributions, and we can see here is our, this should actually be our alpha right here, not alpha 1. So here's our alpha, and then over here in the green we're actually going to have our alpha 2, and you can see here this is of course W and this is W1. And what we want to do is we want to look at this portion of the graph where we see to the right of W1 we have a part of alpha and we have part of alpha 1. Okay? And so we can actually see through a little bit of set theory that W is equal to, so W is equal to A union C, and W1 is equal to B union C by definition of, and if alpha 1 is less than alpha, we know by definition of alpha 1 that the integral of L naught across W1 dx is less than or equal to the integral of L naught across W dx, which can then imply that we can substitute the union of B union C in place of W1, and we can substitute in place of W A union C across these integrals, which then implies that the integral of B across B of L naught plus the integral of L naught across C is less than or equal to the integral of L naught across A plus the integral of L naught plus C. And what do we notice? That our integrals across C both vanish. Then this would imply, since the integral of B of L naught is less than or equal to L naught, the integral of L naught across A, in region W, since A is contained in W, then we know L1 divided by L naught is greater than K. And this would imply that L1 dx across the integral of A is greater than K times L naught dx across the integral of A is greater than or equal to K of L naught dx across the integral of B. And if I am mixing up the order with which I should say this, I am so sorry. Then this would also tell us for all x element of complement of W that L1 divided by L naught is less than or equal to K, which would imply that L1 dx integrated across the complement of W is less than or equal to K times L naught dx integrated across complement of W. Since beta is contained in W complement, the result holds for any subset of W complement. We say that W complement intersects W1 is equal to beta. Hence, we have the integral across B of L1 dx is less than or equal to K times the integral across B of L naught dx is less than or equal to K times the integral across A of L1 dx. By adding the integral across C of L1 dx, we get the integral across W1 of L1 dx is less than or equal to K times the integral across W of L1 dx, and this implies that 1 minus beta 1 is less than or equal to 1 minus beta because of our earlier definitions. So, by the definition of the most powerful test, we can conclude that W is the most powerful critical region of size alpha.
Okay, so in this video I'm going to be covering an extension onto Will's proof of the Neyman-Pearson lemma. Specifically, I'll be covering the corollary 8.3.13 that speaks to the sufficiency of the Neyman-Pearson lemma. Moreover, effectively the way that this works is it says that if we have some particular test statistic which is sufficient. For example, we have t of x, and is sufficient for a parameter called theta. In some cases, people use mu. And moreover, not only is it sufficient, but we have that mass. We know the mass function for it, or the density function for it, at that corresponds to the different thetas, the different parameters at indexes 0 and 1. Then we'll have what's called a uniformly most powerful level alpha test if these conditions are met. And we're going to need a few objects in order to do this actual proof. So first off, we need the Neyman-Pearson lemma from Will's proof. Secondly, we need to kind of inspect what the conditions actually say. Our test statistic t, and remember this is something based off of our random sample, it's going to fall within the rejection region S if g of t given theta 1 is greater than k times g of t given theta naught. And it'll fall into the complement of S, or not the rejection region, if g of t given theta 1 is less than k times g of t given theta naught. Now this is for some k that's greater than or equal to 0, with the alpha level corresponding to this probability here. Okay. Now we want to suppose that we have some test, and we want to interpret this test in the context of the original sample. So the test based on t had a rejection region of R. So the first thing we want to do is inspect the factorization theorem. Now, from the Neyman-Pearson lemma, we know that we can take this mass function from the lemma, and from the factorization theorem, we know that we can write this g of t of x given theta I times some positive function h of x. Okay, so the next thing that we're going to do is effectively take the Neyman-Pearson lemma, and we're going to show that by applying this factorization that we're going to be able to arrive at our conclusion statistics here. So to begin with, we want to look at the first condition. Now, in the context of x, we're going to have that x falls into our rejection region R from the lemma. If, and I'm going to write that up here and then start the condition beneath it. So x will fall into our rejection region R if f of x given theta 1. But remember that this is, we can factorize it in this particular way. So this will be equal to g of t of x given theta 1 times some non-zero function h of x. And if this happens to be greater than k times g of t of x given theta naught by the structure of the lemma, then it'll be in our rejection region R. But notice that this part right here, specifically if you leave off the k, we have something that will factor according to our factorization theorem. This is the same as writing f of x given theta naught. And then we have to attach that k on there for good measure. Okay. So here we have a condition that looks almost exactly like what we're supposed to have, and it follows from our lemma from the first part of the video. Now, x will be in the complement of the rejection region if. And this is sort of the same exact thing mechanically. What we're doing is we're examining the second condition. We're going to have f of x given theta 1 from the lemma, but we can factor that. So we'll have g of t of x given theta 1 times h of x being less than k times g of t of x given theta naught in this case times h of x. But we recall that if I take this g and h portion right here, I can end up with f of x given theta naught times k. Okay. Now the next portion we need to recall that for some alpha level that's between 0 and 1, A test with a power function of beta with an input of theta, the population parameter, will have a size alpha. It will be a size alpha test if the supremum of beta of theta is equal to alpha. And I apologize for my stuttering. My cat has decided to jump up on my paper at this moment. So now we know that the probability that x will be in this rejection region is going to be equal to the probability that our specific test is in S, but we already know from the lemma that that is alpha. Hence, if T meets these conditions, then T will be a uniformly most powerful level alpha test. Now, it is important to note that this follows from the sufficiency portion of the Neyman-Pearson lemma, and that it speaks to when we know we have a uniformly most powerful test or not.
Hi, this is Kelly Pemberton, and I'm going to be doing an example using the Neyman-Pearson lemma. The example states, suppose X is a single observation sample from a population with PDF f of X equals theta x to the theta minus 1 for 0 is less than X is less than 1. We want to find a test with the best critical region, or BCR, that is, find the most powerful test with significance level alpha equals 0.05 for testing the simple null hypothesis where theta is equal to 3 against the alternative hypothesis where theta is equal to 2. Okay, so first we need to verify where our hypothesis, or whether our hypotheses are simple or not. Okay, both our null hypothesis and our alternative hypothesis use this equal form, so they are in fact simple. This means that we can apply the Neyman-Pearson lemma to find the most powerful test by using our likelihood test of theta 1 over our likelihood test of theta 0 greater than k. In this case, our null hypothesis tells us that theta is equal to 3. Our alternative says that theta is equal to 2. So if we plug that in, we're going to have L2 over L3 greater than k. If we substitute this into our likelihood function, which, just a reminder, means that L is equal to equals 1 to 1 of our function x of I theta, which we've already acknowledged what f of x is equal to when reading our example. If we plug this in, we are going to get 2x to the 2 minus 1 over 3x to the 3 minus 1 greater than k. Simplifying this gives us 2x over 3x squared greater than k, in which we can further simplify that to say 2 over 3x is greater than k. In order to get that into the form of x, we manipulate that, and that gives us x is less than or equal to 2 over 3k. And we are going to call this, or allow this to represent K star. Right? So this lemma tells us that the critical region can be represented by W, where X is less than or equal to K star. So next we have to find the value of K star such that its significance level is what was mentioned in this example, which was alpha 0.05. Let's look at what this means, level of significance. Can be defined as alpha equals the probability that X lies within this W given the null hypothesis. Well, plugging in what we know, 0.05 is equal to the probability that we just determined what W was. So X is less than K star, given that theta is equal to 3. We know that we can find the probability using integration. So 0.05 equals the integral from 0 to K star of f of x dx. And what is our function? Well, just a minute ago, when we simplified up here, we determined that plugging in our theta equals 3 gives us a function of 3x squared. So let's plug that in to K star of 3x squared dx. Let's integrate this. So I have 3x cubed over 3 integrated from 0 to K star is going to be equal to my 0.05. Well, the 3's reduced out. I plug in my K star here. Of course, 0 cubed is still going to be 0. So I actually have K star cubed is equal to 0.05. Taking the cube root of both sides, I find that K star is equal to 0.368. So if we substitute this into our critical region that we identified up here, we can say that the rejection region of the most powerful test is X is less than 0.368. Thank you.
Hello guys, today we're going to talk about the UMP normal test, which is the uniformly most powerful test. Now, for this given problem right here, we're going to find the C and find the N if alpha is equal to 0.05 and beta is also equal to 0.05. On this part right here, we're going to look for the probability to reject when we shouldn't reject. And on this second part right here is the probability that we don't reject when we should reject. We're going to go ahead and use the formula to find the z-score. Now, as we know, we're going to go ahead and use the information that's given to find the probability of 0.05. So we're going to get z minus 80 divided by 8 divided by square root of n. And since we're looking for the z-score of a sample mean for the left cell, we know this is equal to negative 1.645. Now, for the right cell, it's the same thing, but instead of 80, we're going to use 76. And this is equal to 1.645. The only thing that changes is the positive and negative. Now, we're going to go ahead and solve for C. As we know for the formula before, we have this given formula for the left tail. And for the right tail, we have this. So what we're going to do to the left tail is multiply it by 8 divided by square root of n. And what we're going to do to the right tail is multiply it by negative 8 divided by square root of n. Doing so, for the left tail, it's going to change it to this. And for the right tail, we have this. Now, since we see this is the same as this, we could go ahead and make these equal to each other. And then the steps we did were distribute the negative. We're going to add c to both sides to get the variables together, add 50, add 80 to both sides, and then finally divide by 2 to get the variable by itself. Now that we have the c value, we could go ahead and substitute it into the formula. So we have 78 minus 80 divided by 8 divided by square root of n equals negative 1.645. Now we're going to go ahead and solve for n, and this is going to give us n is equal to 43.2964, and we could approximate to 44 just to make sure everything's okay. Now, testing 80 versus 76 and using the critical region with a sample mean of 78 and a sample size of 44, this also has a significance level of 0.05 and a power of 0.95. The power is the complement of the probability of a type 2 error. Now, this right here is just an example of a UMP test, or uniformly most powerful test.